July 14, 1943. Sicily, the Simeto River. Dawn is still 2 hours away. The water moves black and slow beneath the broken stone of what used to be a bridge. On the northern bank, German machine gunners wait in the dark, listening. On the southern side, 37 men from the Royal Engineers work in near silence, their hands moving by memory and moonlight. Steel panels slide into place. Pins drop through holes. And then the wire, high-tensile steel wire, no thicker than a man's finger, gets threaded through connection points and twisted tight. Each twist locks 2 tons of panel to the frame. Each panel connects to the next. The structure grows outward over the void, cantilevered into empty air, held together by pins and wire that came from a design sketched in a British garage 5 years earlier. A sergeant checks his watch. 4 hours of work. 16 hours remain. By dawn, this bridge must hold 40 tons. By dawn, the Shermans roll, or the advance stops here. The wire holds. To understand what happened on that riverbank in Sicily, you have to go back to the previous war. In 1918, the Western Front had been a graveyard for bridges. Rivers like the Somme, the Marne, the Meuse, they became barriers that defined the pace of advance and retreat. Engineers built pontoon bridges under fire, lashed timber together, sank pilings into mud. Most of these structures took days to assemble. Many collapsed under the weight of supply wagons or the vibration of artillery. Some were destroyed by a single well-placed shell before a single vehicle crossed. The British Army learned hard lessons. Bridges were bottlenecks. Bottlenecks were death. But between the wars, military engineering stagnated. Budgets shrank. Peacetime thinking took over. The bridges used in training exercises during the 1930s were nearly identical to those used in 1918. Heavy, slow to build, requiring skilled labor and specialized materials. Steel trusses had to be riveted on site. Timber had to be cut to specification. Pontoons required boats, anchors, and calm water. Nobody had solved the central problem. How do you build a strong bridge fast, with unskilled men under fire, using parts you can carry in a truck? In 1936, a civil engineer named Donald Coleman Bailey was thinking about exactly that problem. He wasn't a soldier. He had never seen combat. He worked for the War Office in Sheffield, designing fortifications and analyzing structural loads. But Bailey had a habit of sketching solutions to problems nobody had asked him to solve. He filled notebooks with bridge concepts, modular designs, prefabricated panels, pinned joints that required no welding or bolting. His idea was simple. What if a bridge was like a children's construction toy? What if you could build it from identical panels, light enough for 6 men to carry, strong enough to hold a tank, and simple enough that soldiers could assemble it without engineers? He drew it on paper first. Panels 10 feet long, 5 feet high, made of welded steel lattice. Each panel would weigh 600 pounds. Panels would connect with steel pins dropped through holes at the corners. Horizontal and vertical bracing would lock the structure into a rigid truss. The deck would rest on top, and the whole assembly would span a river in sections, built outward from one bank like a steel arm reaching into space. It was elegant. It was cheap. And for 3 years, almost nobody cared. The War Office filed his drawings. Bailey went back to his other work. The British Army continued training with the same old bridging systems, and the world moved closer to war. Then, in September 1939, Germany invaded Poland. In May 1940, the Wehrmacht tore through France, and suddenly the British Army was evacuating from Dunkirk, leaving nearly all its heavy equipment on the beaches. When Britain began rebuilding its forces, the question came back with new urgency. How do you move armor across blown bridges in hostile territory? Bailey's drawings were pulled from the files. In late 1940, a prototype was authorized. By early 1941, test panels were being fabricated in a workshop in Christchurch. The first experimental bridge was assembled across a gap in a field, then loaded with sandbags to simulate the weight of tanks. It held. The breakthrough came not in theory, but in demonstration. In the spring of 1941, senior officers from the Royal Engineers gathered at the experimental bridging establishment in Christchurch to watch a test. A Bailey bridge span, 30 feet long, assembled in under an hour by a squad of 8 men, was loaded with progressively heavier weights. First, trucks, then a Valentine tank, then sandbags stacked to simulate the weight of a Churchill infantry tank, the heaviest armor Britain was producing. The bridge didn't buckle. The panels didn't separate. The pins held. The wire, threaded through specific connection points and tensioned by hand, kept the panels locked together under dynamic load. When a truck rolled across at speed, the structure flexed slightly, then returned to shape. It was alive, responsive, but stable. The officers were impressed, but they weren't convinced. Skepticism ran deep. The British Army had experimented with modular bridging before: collapsible trestles, sectional pontoons, folding spans, and most had failed in field conditions. Engineers worried that the Bailey design was too light, that the pins would shear under sustained load, that the panels would warp in heat or crack in cold. Bailey answered every objection with mathematics and testing. He calculated load distribution across the lattice. He tested the tensile strength of the wire under fatigue. He demonstrated that panels could be double or triple stacked for heavier loads, that the same components could build a 10-foot span or a 200-foot span, and that damaged panels could be swapped out in minutes without dismantling the entire structure. By summer 1941, the design was approved for production. Factories across Britain began fabricating panels. The steel came from Sheffield. The pins were forged in Birmingham. The wire, the critical, often overlooked component that held the whole system together, was sourced from suppliers who had been making high-tensile cable for aircraft and suspension bridges. This wasn't ordinary wire. It was drawn steel, heat-treated, tested to a breaking strength far beyond what the bridge would ever experience in normal use. It had to be. The wire didn't just connect panels. It resisted shear forces, absorbed vibration, and kept the structure rigid when tanks rolled across at speed. If the wire failed, the bridge collapsed. Bailey obsessed over this detail. He tested wire from different manufacturers, compared fatigue resistance, analyzed how the wire behaved when threaded through holes in cold-rolled steel panels. He specified the exact diameter, the exact tensile rating, the exact method of threading and tensioning. To most observers, it seemed like overkill. To Bailey, it was the difference between a bridge that worked and a bridge that killed people. Production accelerated. By late 1941, enough panels and components were being stockpiled for the first operational deployments. Training programs were established. Infantry engineers practiced assembly drills in camps across England. The goal was to get the time down: 30 feet in 1 hour, 60 feet in 2 hours, 100 feet in 4 hours. In early 1942, the first Bailey bridges were shipped to North Africa. British forces were fighting Rommel across Libya and Egypt, and the Desert War was a war of mobility. Rivers were rare, but wadis, dry riverbeds that flooded suddenly, were common. Engineers needed bridges that could be dropped into place fast, support armor, and be recovered when the front moved. The Bailey proved itself immediately. Bridges were erected across wadis, over blown culverts, spanning gaps in roads cratered by bombing. Sappers assembled them under air attack, sometimes at night, sometimes while the enemy was still in sight. The speed was revolutionary. What used to take 3 days now took half a day. Reports came back to London. It works. It's faster than anything we've ever used. We need more. By mid-1942, production was running at full capacity. By early 1943, Bailey bridges were in every theater where British forces operated. And in July 1943, they were about to face their biggest test yet. Not in the desert, but in Europe, where rivers ran deep and the enemy was dug in. The genius of the Bailey Bridge wasn't in what it added. It was in what it removed. Traditional military bridges required specialized joints, rivets, bolts, welds. Each joint was a point of failure, and each required skilled labor and tools. Bailey eliminated all of it. His system used only 2 types of fasteners: pins and wire. The pins were steel rods, tapered at one end, dropped vertically through holes at the corners of each panel. Gravity held them in place. The wire was threaded through smaller holes at specific points along the panel edges, then twisted tight by hand using a simple tool. The panels themselves were marvels of efficient design. Each was a welded lattice of steel tubes and flat bars, forming a truss 10 feet long and 5 feet high. The lattice distributed load across the entire structure. When weight pressed down on the deck, the top chord of each panel went into compression, and the bottom chord went into tension. The diagonal bracing transferred force between chords, and the wire locked adjacent panels together so they acted as a single rigid beam. This was bridge building as assembly, not construction. No measuring, no cutting, no welding. A panel either fit or it didn't. A pin either dropped through or it didn't. There was no room for improvisation, and that was the point. Simplicity meant speed. Speed meant survival. The modular nature of the system allowed infinite variation. A single truss bridge could span 30 feet and carry light vehicles. A double truss bridge, 2 panels wide, bolted side by side, could span 60 feet and carry medium tanks. A triple truss bridge could span 100 feet and carry anything the Allies had, including the 40-ton Sherman. And if the span was too long for the load, you didn't need a different bridge. You just added another layer of panels on top, double-stacked, triple-stacked, using the same pins, the same wire, the same assembly process. It was scalable, repairable, and endlessly adaptable. Steel wire doesn't sound like a critical component. It sounds like an afterthought. But in the Bailey Bridge system, it was everything. The wire used in Bailey bridges was high-tensile steel, drawn and heat-treated to a breaking strength of over 100,000 pounds per square inch. That's stronger than most structural steel. It had to be, because the wire wasn't just holding panels in place. It was resisting dynamic shear forces generated by moving loads. When a 40-ton tank rolls across a Bailey bridge at 10 miles per hour, the structure flexes. The deck sags slightly under the weight, and the panels shift relative to each other. Without the wire, the pins would rattle in their holes, the panels would separate, and the bridge would collapse. The wire kept everything tight. It absorbed micro-movements. It turned 20 separate panels into one continuous beam. Sourcing this wire was a challenge. In 1941, Britain was under blockade. Steel production was prioritized for ships, planes, and guns. High-tensile wire was used in aircraft control cables, suspension bridges, and anti-submarine nets. Bailey had to compete for supply, and he had to prove that his bridges were worth the allocation. He did. Testing showed that the wire outlasted the panels. Even after a bridge had been assembled, disassembled, transported, and reassembled multiple times, even after months of exposure to rain, mud, and salt, the wire retained its strength. It didn't corrode easily, because it was drawn smooth and coated with a thin layer of oil. It didn't fatigue easily, because the loads were intermittent, and the wire was over-engineered by a factor of 3. In some ways, the wire was the most elegant part of the design. It was simple, cheap, and nearly indestructible. It required no special tools to install, just a threading rod and a twist. And yet it was the component that made everything else work. Donald Bailey was not a charismatic man. He was quiet, methodical, and deeply skeptical of grand gestures. Colleagues described him as reserved, even shy. He didn't seek attention. He didn't lobby for his ideas. He simply worked, and trusted that good design would speak for itself. Born in 1901 in Rotherham, Yorkshire, Bailey studied civil engineering at the University of Sheffield. He graduated in 1923, during the post-war economic slump, and spent the early years of his career designing railway infrastructure and municipal buildings. It was unglamorous work, but it taught him to think in terms of load, stress, and economy. Every project had a budget. Every design had to be justified in pounds and pence. In 1928, he joined the War Office as a civil servant, assigned to the experimental bridging establishment. His job was to evaluate bridge designs submitted by military engineers and civilian contractors. Most of them were terrible. Overweight, overcomplicated, too expensive to produce in quantity. Bailey didn't criticize. He just started sketching his own ideas in the margins of reports. For years, nobody paid attention. But Bailey kept refining the concept. He built small models out of matchsticks and thread. He calculated load paths on scraps of paper. He thought about how soldiers, tired, cold, possibly untrained, would actually assemble the bridge in the field. He obsessed over the question, what is the simplest thing that could possibly work? When the War Office finally gave him a chance to build a prototype, Bailey didn't oversell it. He presented the numbers, demonstrated the assembly process, and answered questions. When officers expressed doubt, he didn't argue. He built another test span and invited them to watch it hold weight. His persistence paid off. By 1943, Bailey bridges were everywhere, and Bailey himself was traveling to war zones to train engineers and troubleshoot problems. He never wore a uniform. He was still a civil servant, still quiet, still methodical. But soldiers in Sicily and Normandy knew his name, because his bridge was the reason they were still moving forward. In warfare, permanence is a luxury. Speed is a necessity. Before the Bailey Bridge, military engineers built bridges to last. They sank pilings into riverbeds, erected timber trusses, poured concrete abutments. These were strong, stable structures, but they took days to build, and they couldn't be moved. If the front shifted, if the river flooded, if enemy artillery found the range, the bridge became a liability. The Bailey changed the calculation. It wasn't designed to be permanent. It was designed to be fast, portable, and expendable. A Bailey bridge could be erected in hours, used for days or weeks, then disassembled and trucked to the next river. If it was damaged by bombing, engineers could replace a few panels and have it operational again within hours. If it was no longer needed, it could be pulled down in a morning and stockpiled for the next advance. This tactical flexibility was revolutionary. Armies could move faster because they weren't tied to fixed infrastructure. Supply lines could adapt to changing front lines. Armored divisions didn't have to wait for engineers to build a bridge. They rolled up, and the bridge was already going up. The speed advantage was compounded by simplicity. Bailey bridges didn't require specialist equipment. No cranes, no pile drivers, no concrete mixers. Just trucks to carry the panels, and soldiers to assemble them. A trained engineer platoon could have a 60-foot bridge up in under 3 hours. An untrained infantry squad, given basic instruction, could do it in 5. This mattered enormously in fluid combat situations. In North Africa, battles moved across hundreds of miles in weeks. In Italy, rivers cut through every valley, and every valley was contested. In Northwest Europe, the race to Germany meant crossing dozens of rivers, canals, and blown road bridges. The Bailey Bridge turned obstacles into delays, and delays into mere pauses. German forces, by contrast, relied on heavier bridging systems. Brückengerät, pioneer bridging trains, pontoon ferries, that required more time and more specialized personnel. When Allied forces destroyed a bridge, German engineers often needed days to restore crossing capability. When German forces destroyed a bridge, Allied engineers had it back up by the next day. Morning speed became a weapon in itself. A weapon is only as good as the logistics that sustain it. The Bailey Bridge had a logistical elegance that matched its engineering simplicity. Every panel was identical. Every pin was interchangeable. Every bridge used the same components in different configurations. This meant that supply chains could be streamlined. Factories didn't have to produce dozens of specialized parts. They mass-produced a handful of standardized items. Panels were stamped and welded on production lines. Pins were forged in batches of thousands. Wire was drawn and coiled in bulk. By 1943, British factories were producing enough components to build over a mile of bridging per week. These components were crated, loaded onto trucks and ships, and distributed to every theater of war. Storage was simple. Panels could be stacked flat. Pins could be bundled. Wire could be coiled. A single 3-ton truck could carry enough components for a 30-foot bridge. A convoy of 10 trucks could carry enough for a 200-foot span. This meant that engineer units could pre-position bridging assets near anticipated crossing points, reducing the time between bridge destroyed and bridge rebuilt. Maintenance was minimal. Panels didn't rust easily because they were coated with bitumen paint. Pins didn't wear out because they weren't subject to friction. Wire could be inspected visually. If it looked intact, it was intact. Damaged components were swapped out, not repaired. A panel with a cracked weld was pulled from service and replaced with a fresh one from the stockpile. This repairability extended the life of the system. A Bailey Bridge built in 1942 could be disassembled in 1943, transported to a new location, reassembled, used again, disassembled again, and still be functional in 1945. Some bridges were erected, torn down, and re-erected a dozen times over the course of the war. The economic advantage was staggering. Traditional military bridges were often abandoned after use because they couldn't be recovered. Bailey bridges were recovered, reused, and reallocated. This reduced waste, stretched budgets, and ensured that frontline units always had bridging capability. The Bailey Bridge wasn't the only military bridge system in World War II, but it was the best. Germany used several bridging systems, the most common being the Brückengerät B and Brückengerät C. These were sturdy, well-engineered bridges, but they were heavy and slow to assemble. The Brückengerät B required a truck-mounted launching mechanism and could take 6 hours to span 50 feet. The Brückengerät C was modular, but its components were heavier than Bailey panels, and it required more personnel to assemble. The United States developed the M2 Treadway Bridge, a floating pontoon system that could be assembled quickly across calm water. It was excellent for wide, slow-moving rivers, but it struggled in fast currents, and it couldn't support the heaviest armor without additional reinforcement. The U.S. also used the British Bailey Bridge extensively, recognizing that it was superior for rapid assault bridging. The Soviet Union relied primarily on wooden pontoon bridges and improvised timber trusses. Soviet engineers were skilled and resourceful, but their bridging systems were labor-intensive and required large engineer battalions. The Soviets didn't adopt the Bailey Bridge during the war, but they studied it carefully, and post-war Soviet bridging systems borrowed heavily from Bailey's modular design principles. Japan's military bridging was limited and outdated, relying on pre-war designs that struggled with the weight of modern armor. Japanese forces rarely operated heavy tanks, so their bridging doctrine prioritized light infantry and supply vehicles. The Bailey Bridge stood out because it combined speed, strength, and simplicity in a way no other system did. It was lighter than German bridges, stronger than American pontoons, faster than Soviet timber construction, and more versatile than anything Japan fielded. By 1944, even U.S. combat engineers, initially skeptical of the British design, were requesting Bailey components in preference to American-made alternatives. General Eisenhower himself praised the design, later calling it one of the 3 most important pieces of military equipment of the war, alongside the C-47 transport plane and the Jeep. July 14, 1943. Sicily. The Simeto River crossing. The invasion of Sicily, Operation Husky, was 3 days old. British and American forces had landed on the southern coast and were pushing inland, racing to capture the port of Catania and cut off Axis retreat routes to the Italian mainland. But between the landing beaches and Catania lay the Simeto River, a natural defensive line the Germans had fortified and prepared to hold. German engineers had blown the Primosole Bridge 2 days earlier. The stone arches collapsed into the river, leaving a gap 100 feet wide. The current was strong, the banks were steep, and German positions on the northern side overlooked the entire approach. Machine gun nests were dug into the hillsides. Mortar teams had pre-registered coordinates on the river crossing. Snipers waited in the ruins of a farmhouse 300 meters back. The British 8th Army needed that crossing. Without it, armor couldn't move forward. Without armor, infantry couldn't break through. Without a breakthrough, the entire operation stalled. At 2200 hours on July 13th, a platoon from the Royal Engineers arrived at the southern bank with 6 trucks loaded with Bailey Bridge components. 37 men, 80 panels, 200 pins, coils of high-tensile wire, and orders to have the bridge operational by dawn. They worked in near darkness. Moonlight reflected off the water, but clouds kept drifting across, plunging the riverbank into blackness. The engineers couldn't use electric lights. German observers would call in artillery within minutes. So they worked by feel, by memory, by the rhythm of assembly drills they'd practiced 100 times in training. First, the launching nose, a lightweight truss section that extended the bridge outward from the bank, cantilevered over the water. Panels were slid into position, pins dropped through corner holes, wire threaded and twisted. Then the next panel, and the next. The structure grew incrementally, 10 feet at a time, supported by the rigidity of the truss and the tensile strength of the wire. Every 20 minutes, German machine guns opened up. Tracer rounds arced across the water, stitching the far bank. The sappers dropped flat, waited for the fire to stop, then stood and kept working. A corporal took a bullet through the shoulder. 2 privates dragged him to cover, bandaged him, and returned to the bridge. No one spoke much. There wasn't time. By midnight, the bridge was 30 feet long. By 0260 feet. By 0490 feet. The sappers were working in shifts now, some assembling panels, others threading wire, others hauling components forward from the trucks. Sweat soaked through their uniforms despite the cool night air. Hands were bleeding from wire cuts and splinters. But the bridge kept growing. The final section was the hardest. The launching nose had to be lowered onto the far bank and anchored. This required precision. If the alignment was off by more than a few inches, the panels wouldn't seat properly, and the bridge would twist under load. The engineers used hand signals, adjusting the angle degree by degree, until the nose settled into place. At 05:30, the last pin was driven. The last wire was twisted tight. The deck planking was laid. The bridge was complete, 100 feet, 40 tons of steel, assembled in 7 hours. At 600, the first Sherman tank rolled onto the bridge. The driver moved slowly, feeling the structure flex beneath 38 tons of armor and fuel. The bridge sagged slightly, held, then settled. The tank reached the midpoint, the moment of maximum stress, and kept moving. Across the water, onto the northern bank, behind it, 5 more Shermans, then half-tracks, then supply trucks. The bridge held them all. By 0700, the crossing was secure. Infantry had pushed forward under cover of the tanks, cleared the German positions on the hillside, and established a perimeter. The advance continued. The Bailey Bridge at Primosole stayed in place for 3 weeks, carrying thousands of vehicles and tens of thousands of soldiers. It was never damaged. It never needed repair. When the front moved north, engineers disassembled it in a single afternoon and trucked the components to the next river. The success at Primosole was not an isolated victory. It was a proof of concept that rippled through every Allied army. Throughout the Italian campaign, from Sicily through the mainland, up the spine of the Apennines toward Rome, Bailey bridges became the standard solution for river crossings. Engineers erected them across the Volturno, the Garigliano, the Rapido. Each time the process was the same: panels, pins, wire, speed. Each time the bridges held. But the true test came in 1944, during the invasion of Normandy and the subsequent breakout into France. On June 6, 1944, Allied forces landed on 5 beaches in Normandy. Within days, engineers were building Bailey bridges over streams, canals, and blown road crossings throughout the Bocage, the dense hedgerow country of northern France. These weren't major rivers. They were small watercourses, 10 to 30 feet wide, that had been cratered by German demolitions or bombed by Allied aircraft. Each gap was a bottleneck. Each bottleneck delayed the flow of supplies to frontline units. And in the fast-moving breakout battles of July and August 1944, delays meant casualties. Bailey bridges eliminated the delays. Engineer battalions traveled with preloaded bridge trucks, staying just behind the advancing armor. When a Sherman column hit a blown bridge, engineers moved up, assessed the gap, and started building. In many cases, the bridge was complete before the infantry had cleared the far side. The speed was extraordinary. At the town of Gavras, south of Caen, engineers erected a 70-foot Bailey bridge across the Odon River in under 4 hours, while German artillery shelled the crossing. At Argentan, during the closing of the Falaise pocket, a Bailey bridge was built across a canal under small arms fire, with German forces less than 500 meters away. At Chartres, engineers used Bailey panels to repair a partially destroyed stone bridge, adding a steel span where the center arch had collapsed. By September 1944, Allied forces were approaching the German border. The Rhine River, the greatest natural barrier in Western Europe, loomed ahead. Crossing the Rhine would require bridging on a scale never attempted before. On March 7, 1945, American forces captured the Ludendorff Bridge at Remagen, a rare intact crossing over the Rhine. But the bridge was damaged and unstable, weakened by German demolition charges that had partially detonated. Engineers reinforced it with Bailey bridge sections, adding steel trusses to distribute load and prevent collapse. For 10 days, the Remagen Bridge carried the entire weight of the Allied advance into Germany, and the Bailey panels were critical to keeping it operational. Elsewhere along the Rhine, where bridges had been completely destroyed, engineers built Bailey spans as temporary crossings, while heavier pontoon bridges were constructed. At Wesel, at Oppenheim, at Mainz, wherever the Allies forced a crossing, Bailey bridges followed within hours. Field Marshal Bernard Montgomery, commanding British forces in Northwest Europe, made a point of visiting Bailey Bridge sites. He watched sappers work under fire, saw tanks roll across spans erected overnight, and recognized that logistics, not firepower, was determining the pace of the advance. In a letter to the War Office in April 1945, he wrote, "Without the Bailey Bridge, we would not be in Germany." General Dwight D. Eisenhower, Supreme Commander of Allied forces in Europe, went further. After the war, he was asked to name the most important pieces of equipment that won the European campaign. He listed 3: the Douglas C-47 transport aircraft, the Willys Jeep, and the Bailey Bridge. Not tanks, not bombers, a bridge. Because the bridge was what kept the army moving. It was what turned rivers from barriers into pauses. It was what allowed supply trucks to follow combat units without delay. What allowed armor to exploit breakthroughs without waiting for engineers to catch up. The Bailey Bridge didn't win battles by itself, but it won the logistical race that made victory possible. By May 1945, over 3,000 Bailey bridges had been erected in the European theater alone. Some were 30 feet long, some were over 200 feet. Some carried light vehicles, some carried 70-ton Churchill tanks. All of them were built from the same panels, the same pins, the same wire. And at the center of each bridge, threaded through connection points, twisted tight by hand, invisible to anyone who didn't know to look for it, was the wire that Donald Bailey had obsessed over in 1940. High-tensile steel, over-engineered by a factor of 3, holding 40 tons without complaint. The wire that made it all possible. The war in Europe ended on May 8, 1945. The war in the Pacific ended 3 months later. But the Bailey Bridge kept working. In post-war Germany, thousands of bridges lay in ruins. The Allies had bombed them. The Germans had demolished them during retreat. The Rhine, the Elbe, the Danube, every major river in Central Europe had been severed. Civilian populations were cut off from food supplies. Refugees couldn't return home. Relief convoys couldn't move. Bailey bridges filled the gaps. Military engineers erected temporary spans across bombed-out rivers, allowing humanitarian aid to reach devastated cities. Some of these bridges stayed in place for years, carrying civilian traffic while permanent reconstruction was planned and funded. In some cases, the Bailey Bridge was the permanent solution, reinforced, anchored, and left in place indefinitely. The same pattern repeated across Europe. In France, in the Netherlands, in Italy, wherever infrastructure had been destroyed, Bailey bridges provided the immediate restoration of connectivity. They weren't elegant, they weren't beautiful, but they worked, and they worked immediately. In Britain, Donald Bailey was awarded a knighthood in 1946 for his contribution to the war effort. He accepted quietly, with characteristic modesty. In interviews, he deflected praise, emphasizing that the bridge was a team effort. Engineers, fabricators, soldiers in the field. He never claimed sole credit, even though the design was entirely his. Post-war military analysis confirmed what field commanders had known since 1943. The Bailey Bridge was the most effective military bridge system ever developed. The U.S. Army adopted it as standard equipment. The Canadian Army did the same. France, Belgium, the Netherlands. Every NATO country stockpiled Bailey panels and trained engineers in their use. But the system's influence extended far beyond military use. In the late 1940s and early 1950s, Bailey bridges began appearing in civilian disaster relief efforts. When floods washed out bridges in Britain, emergency services used Bailey spans to restore access. When earthquakes destroyed infrastructure in Greece and Turkey, relief organizations erected Bailey bridges to reconnect isolated villages. The design was so effective that commercial engineering companies began producing civilian variants. In 1948, a British firm called Callender Hamilton purchased rights to manufacture Bailey-type panels for civilian use. Other companies followed. By the 1950s, Bailey-type modular bridging was available worldwide, used for everything from temporary construction access to permanent rural crossings in developing countries. The Korean War, which began in 1950, proved the system's continued relevance. United Nations forces, primarily American, British, and Commonwealth troops, used Bailey bridges extensively throughout the peninsula. Rivers in Korea were swift and rocky, often impassable except at fixed crossing points. When North Korean and Chinese forces destroyed bridges during retreats, UN engineers rebuilt them with Bailey spans, often within 24 hours. One notable example occurred in December 1950. During the retreat from the Chosin Reservoir, U.S. Marines, surrounded and withdrawing under heavy enemy pressure, reached a blown bridge over a ravine at Funchalen Pass. Without the bridge, the entire division, 15,000 men and their equipment, would be trapped. Engineers airdropped Bailey Bridge sections by parachute, assembled a span under fire in freezing temperatures, and enabled the Marines to escape encirclement. The bridge held for 3 days under continuous traffic, carrying tanks, trucks, and thousands of troops, before being abandoned as UN forces withdrew south. By the 1960s, the Bailey Bridge had become a global standard. Over 70 countries adopted the system. The basic design remained unchanged: panels, pins, wire, But manufacturers developed variations for specific needs: heavy-duty panels for extra heavy loads, lightweight panels for rapid deployment by helicopter, floating pontoon supports for wide rivers. Each variation followed Bailey's original principles: modularity, simplicity, speed. In the civilian world, Bailey bridges became essential infrastructure in remote and developing regions. In India, engineers used them to span rivers in the Himalayas, connecting mountain villages that had never had road access. In Africa, relief organizations used them to restore supply routes after floods and conflicts. In South America, mining companies used them to access remote sites where permanent bridges weren't economically viable. The bridges proved remarkably durable. Some Bailey bridges erected in the 1950s remained in service into the 21st century, carrying daily traffic for over 50 years. The steel panels, if maintained and repainted, didn't degrade. The pins didn't wear out. The wire, if replaced periodically, continued to hold the structure together. In 1985, a major earthquake struck Mexico City, destroying or damaging dozens of bridges across the city. Emergency response teams flew in Bailey Bridge components from military stockpiles in the United States, and within a week, temporary crossings were operational across every major gap. The bridges stayed in place for months while permanent reconstruction was completed. In the 1990s, during conflicts in the Balkans, NATO forces used Bailey bridges to restore mobility in war-torn Bosnia and Kosovo. In Afghanistan and Iraq, coalition engineers erected Bailey-type spans to replace bridges destroyed by insurgent attacks. The design that had proven itself in World War II was still proving itself 60 years later, in deserts and mountains half a world away from where it was conceived. Modern variants have refined the system. The British Mabey-Johnson Bridge, developed in the 1970s, uses lighter alloys and improved joints, but the fundamental design is pure Bailey. The American Medium Girder Bridge, adopted in the 1980s, uses square panels instead of rectangular, but the assembly method is identical. The Australian Mooney Bridge, the Indian Sarvatra, the Chinese Type 321, all are descendants of Bailey's original concept. Donald Bailey himself lived to see much of this legacy. He continued working as a civil engineer after the war, designing infrastructure projects in Britain and consulting on bridge systems abroad. He avoided publicity, rarely gave interviews, and declined most invitations to speak at military or engineering conferences. He preferred to work quietly, solving problems, sketching solutions in notebooks. He died in 1985, at the age of 83. His obituary in The Times described him as the man who built the bridges that won the war. It was hyperbole, but not by much. Production numbers tell part of the story. During World War II, British factories produced over 200 million pounds of Bailey Bridge components, enough to build over 3,000 bridges, totaling more than 200 miles of span. The United States manufactured an additional 150 million pounds under license. After the war, production continued, and by the year 2000, an estimated 500 million pounds of Bailey-type bridging had been produced worldwide. That's enough steel to span the Atlantic Ocean. Twice. But the true measure of the Bailey Bridge isn't in tonnage. It's in the moments when it mattered. The Sherman tank rolling across the Sicily River at dawn. The Marine convoy escaping Chosin Reservoir in sub-zero cold. The relief truck crossing a ravine in the Himalayas, carrying food to a village cut off by flood. Every one of those crossings depended on the same simple system: panels, pins, and wire. The wire that held the pins that locked the panels that carried the weight. The wire was the part nobody saw. It was the detail hidden inside the structure, threaded through holes, twisted tight, invisible unless you knew to look for it. But without it, nothing worked. Donald Bailey knew that. He knew that engineering greatness wasn't in grand gestures or revolutionary materials. It was in getting the small things right. The tolerances, the connections, the wire. The wire that came from a Sheffield steel mill, drawn and heat-treated to a breaking strength far beyond what it would ever face. The wire that was threaded through panels by soldiers with bleeding hands, under fire, in the dark. The wire that held 40-ton tanks suspended over rivers and never broke. That wire, high-tensile, over-engineered, obsessed over by a quiet civil engineer who thought in tolerances and safety factors, that wire changed the course of the war, not by itself, but without it, the bridge didn't work. And without the bridge, the advance stopped. There is a paradox at the heart of great engineering. The more complex the problem, the simpler the solution must be. The Bailey Bridge solved one of the oldest problems in warfare: how to cross a river under fire, with a system so simple that untrained soldiers could build it in darkness. It didn't require genius to assemble. It didn't require heroism. It just required following the process: panel, pin, wire. Repeat until the river is crossed. But that simplicity was the product of obsessive complexity. Donald Bailey spent years refining tolerances, testing materials, calculating load paths. He obsessed over the wire, its diameter, its tensile strength, the exact method of threading it through panels. To most people, wire was an afterthought. To Bailey, it was the linchpin, the detail that made everything else work. That's the lesson of the Bailey Bridge. Innovation isn't always radical reinvention. Sometimes it's incremental refinement. Sometimes it's solving a problem not by adding complexity, but by removing everything unnecessary until only the essential remains. Panels, pins, wire. 3 components. Infinite possibilities. The Bailey Bridge didn't end wars. It didn't fire a shot. But it kept armies moving when rivers tried to stop them. It carried soldiers forward when roads were destroyed. It turned obstacles into pauses, and pauses into momentum. And it did all that with steel, geometry, and a wire no thicker than a man's finger. Threaded through holes, twisted tight, holding more than metal. Holding the weight of history. The wire held. The bridge stood. The advance continued. And somewhere in the mud of a Sicilian riverbank, in the frost of a Korean ravine, in the dust of a Himalayan valley, that wire is still there. Quiet, invisible, unbreakable, doing exactly what Donald Bailey designed it to do. Holding the world together, one twist at a time.